Well, good afternoon, and thank you for joining me on this journey through time and space. My name is Angus, and I'll be your guide to three major attractions along the way. So first, we are going to look at how the modern space industry is changing and why open source software has a critical role to play in that evolution. Next, we'll consider why Rust is the perfect language for complex, high-stakes use cases like space mission simulation. And I know I'm kind of preaching to the hive mind here. It's a bit like asking the Borg how they feel about the Borg. I was tempted to include a slide that just said, Rust good, and leave it at that. But we'll do things by the book. Then in the second half, we'll explore a real space mission simulator written with Rust. And I'm aiming for you to leave knowing, firstly, how to model all of time with femtosecond precision in 7 astronomical timescales, and 2, why this matters for the future of space exploration. I promise you won't need a physics PhD to understand any of this. It's not rocket science. So let's kick things off by making some simulated astronauts very uncomfortable. I'm a software engineer, not a doctor. I don't have any formal education in astrophysics, and in my spare time, I teach Rust on my site, howtocodeit.com. So if you're wondering what credentials I have to be talking to you about space mission simulators, don't worry, I had the same question. So when I was approached for this project, the lead told me that they just needed skilled Rust engineers. But I thought, better safe than sorry. I will ask, are you sure I won't need a background in astrodynamics? And he said yes. And that was a lie. So the last year has been quite uncomfortable for me, not because astrodynamics is excessively complex, but because historical astrodynamics code is accidentally complex. And to show you how Rust is bringing balance to the force, let's establish some context. I am a core team member for Ephemerista, which is a new open source space mission simulator. It is wholly funded by the European Space Agency, ESA, and maintained by the LibriSpace Foundation, which is a non-profit for the promotion of open source hardware and software in space. So when complete, Ephemerista will include GUI mission planning and analysis tools, a Python API tailored to flight dynamics engineers and mission analysts, and pluggable integrations with a huge suite of existing tools which prop up the industry. And this is all backed by LOX, an ergonomic Rust astrodynamics library. And to understand why ESA would be interested in funding such a thing, we need to know a bit about what we're simulating and the showdown currently happening in low Earth orbit. Now, an astrodynamics library has more responsibilities than can comfortably fit into one talk, but here are the biggies. Navigation. We would like to know how to get from A to B, where A and B move in 3 dimensions and may be so massive that they alter the flow of time itself. Maneuvering, also important. Getting from A to B takes a certain amount of fuel, and to calculate that, we need what's known as a delta V budget, which is the total change in velocity from the maneuvers we perform along the way. Comms, of course. After launching our payload into space, we need to communicate with it, and for that, we need to know the link budget of a mission. And, of course, collision avoidance. We would ideally like to know how not to crash our multi-million-dollar spacecraft into someone else's multi-million-dollar spacecraft. By the way, certain spacefaring groups and organizations not terribly fussy about that last one, which puts greater pressure on everyone else to model and react to someone muscling into our orbits. And spaceflight, as you can probably tell, necessarily involves a lot of testing in prod. But without mission simulators, each launch would be equivalent to sticking your finger in the air and hoping for the best. And for the visual learners, I have demonstrated this graphically. Here we see that through simulation, Ferris has identified a critical vulnerability in plans for the galaxy's most expensive orbital death machine, giving his employer the opportunity to correct the design before going to build. Of course, we've all seen the documentary, Star Wars Episode 4: A New Hope. We know how it ends, and this is because Ferris works for Boeing. Now, I keep saying next generation, and not just for the Star Trek pun. Space has changed dramatically in the last decade. Private enterprise has entered the ring, and the prize is real estate in low Earth orbit. And ask any billionaire, super yachts? Very 2015. When Musk and Bezos get together to assert their masculinity, they compare the size of their satellite constellations. Constellations are the new hotness. Networks of satellites flying in unison, communicating with each other, and providing global coverage at a fraction of the latencies involved with traditional geostationary orbits. That is a lot of satellites, and it's getting crowded up there. The image here depicts the spacecraft, rocket bodies, and debris that's large enough to name in low Earth orbit alone. And since the number of safe orbits is limited, we essentially have a gold rush in which it is extremely difficult for small players to compete. So if we value open access to space, then high quality, free, open source software is a critical piece of that puzzle. Because commercial mission simulators are hugely expensive. They cost less than a rocket launch, but you'll need a mortgage, not a credit card. Meanwhile, existing open source solutions have tended not to keep pace with the changing nature of space missions. For example, space junk is a massive problem. The image on the right is the debris that is big enough to track, but not big enough to be worth naming. It's trash doing 18,000 miles an hour, and a centimeter-wide piece of space junk will impact other objects with the force of a car at high speed. So the International Space Station orbits at the bottom edge of low Earth orbit and has to maneuver if there's even a 1 in 10,000 chance of collision. Now, cleaning that mess up is a whole new class of mission in which there's a lot of interest right now. But support for missions like these has to be custom built, and that carries substantial development costs. Because a typical mission analyst works at a higher level of abstraction than an astrodynamics library. This is the Python crowd. The people planning the missions are not the same people extending the simulator, and startups who are trying to compete in this industry must be able to do both. And even if they can afford both, combining old tools in new and exciting ways produces new and frustrating failure modes. Pain is trying to debug Java astrodynamics routines from MATLAB. Do not try it. So ESA is interested in sponsoring both open source and commercial initiatives from the dual standpoints of promoting fair access to space and keeping up in an increasingly competitive and fast-changing industry. ESA's 2025 agenda sets out its aim to double its spending on new technologies and, in particular, reduce the time to contract for projects under €1 million, projects like Ephemerista. And that's before you consider the current geopolitical situation, which is perhaps best described as spicy. ESA is very unusual among space agencies in that it has 22 member states, none of which could run a serious space program on their own, but together account for about a third of the global revenues of the space industry. Nevertheless, ESA is highly reliant on cooperation with the US, especially for manned missions, with another agenda item for 2025 being to negotiate with NASA to land the first European on the moon. And that's a direct quote, by the way. Ask NASA if they'll please bring a European on board. And cooperative isn't a trait classically ascribed to Elon Musk, the man who runs the world's largest space company by day and lays off 10% of NASA's workforce by night. Still, a more willing partner than either Russia or China. It is very much in the collective interest that quality open source software for conducting space missions becomes a staple of the new space age. Without it, access to space is conditional on your passport and your politics. So that's the motivation. Now let's explore what makes Rust a better backend for a modern space mission simulator. Fine, I'll tell you what you already know. Good Rust is fast, obviously. If you compare standard astrodynamics algorithms in Rust with their Python equivalents, it's no surprise that Rust comes out on top. So a typical workload is something called orbit propagation, so figuring out where an orbiting body is going to go next. And if you want to propagate many orbits, say because you are flying a satellite constellation, the throughput is directly proportional to the number of threads you can schedule. And comparing parallelized Rust to single-threaded Python is not a fair competition, but we don't want fair, we want fast. And happily, using Rust doesn't rule out Python for users who want access to low-level astrodynamics routines in a language they're comfortable with. So LOX uses the Pyo3 crate to expose Python bindings behind a feature flag, and you'll hear about an interesting challenge that presents in the second half of this talk. But big deal, right? Like Rust didn't invent multi-threading. It didn't even invent safe multi-threading. So what other advantages does it offer? Well, native compilation and portability are highly desirable. So OraKit, the most successful open astrodynamics project to date, is written in Java. So like it or not, the JVM is coming along for the ride. NASA's free simulator, GMAT, is written in C++. And I used to have a really good line about how it doesn't run on Apple Silicon, but they very selfishly went and fixed that. Don't worry, though, if you enjoy shitting on C, and I know that you do, that's all still to come. Most importantly, however, Rust is expressive. Rust is phenomenally good at communicating hardcore domain knowledge to non-specialist developers. And that is the lifeblood of open source projects. Rust is very good at statically preventing you from doing things you didn't know were dangerous. So we like to complain about Rust compile times, but Rust C has a much shorter feedback loop than Git blame. It won't burn out, quit the project, and go live in the hills either. So if you haven't seen Josh Lebo-Fieser's RustConf 24 talk, I highly recommend looking it up. He shares some pretty mind-blowing Rust that Google's Fuchsia OS team used to prevent deadlocks at compile time. So Rust C can prevent you from violating invariants you didn't know existed. And to drive that home, we're going to do some domain modeling of our own. Starting from a philosophical question, we will build up the real prime-time abstractions underpinning the LOX time crate. No one likes going into a coding challenge cold, so I'll ask a gentle warm-up question before we stare directly into the time vortex. What is time? Well, I have a background as a web developer. So as far as I'm concerned, time began on the 1st of January, 1970, and it's been going up in nanoseconds ever since. And if you take this view of time, it fits very nicely inside a single I-64. But there are two opposing problems with this model in the context of a space mission simulator. On one hand, an I-64 is too small. It gives us roughly 18 quintillion nanoseconds to play with, which sounds like a lot, but it's about plus or minus 300 years. And while that might not be long enough to get those astronauts back from the International Space Station, should be enough for most space missions. It's not enough for some space algorithms, though. So astronomers don't use the Unix epoch. Mostly, they use J2000, which began midday, January 1st, 2000. And why midday? Because astronomers hunt at night. But the Julian epoch is also used, and that began 4713 BC. And a qualified astrophysicist will tell you that is more than 300 years ago. And on the other hand, a nanosecond is a long time in physics. Where we have algorithms that are accurate to fractions of nanoseconds, we'd like to be able to represent their output correctly. And we should avoid snowballing rounding errors, since operations like orbit propagation are effectively pipelines of state calculations in which each output is the input to the next iteration. And to be completely honest with you, very few, if any, mission simulations need femtosecond precision. And most algorithms don't guarantee it. But we'll see shortly that femtoseconds can be represented at no extra cost versus a model with nanosecond precision, so we lose nothing from supporting it. If you want algorithms that have that precision, then you're free to use them. So how do we improve on an I64 representation of time? Well, let's start by standing on the shoulders of giants and take inspiration from the time representation used by the International Astronomical Union's Standards of Fundamental Astronomy, a collection of essential astronomy routines written in C and Fortran 77. If you don't know, by the way, Fortran, it's like catnip to physicists. They can neither have nor want nice things. We, however, are going to look at the SOFA C representation, and it's two doubles. It's just straight up two doubles. The time relative to some epoch, usually J2000, is represented as the sum of two 64-bit floating point numbers. And how do you apportion the time between these two doubles, you ask? With great care. Because this is C, where the behavior of your code depends on how well you read the instruction manual and how much you had to drink the night before. The larger the integral part of each double, the fewer decimal places of precision your time supports. And there is a correct way to apportion your time reliably to achieve femtosecond precision. But if you're not up to date on your IEEE 754 floating point arithmetic, how precise your time is will depend on what your time is. Chef's kiss. There is value here, though. With a bit of type-driven Rust, we can codify the good ideas and prevent users from cutting themselves on the sharp edges. First, we take one of those doubles and restrict it to an integral number of seconds relative to J2000. An I64 might not give us enough nanoseconds to play with, but it fits an order of magnitude more seconds than the age of the known universe. And that leaves us to model the fraction of the current second. We initially tried using another I64 to count attoseconds, 10 to the negative 18 seconds since the previous second, but in practice, floating point arithmetic is so fundamental to physics that we'd have increased the complexity of the code while also decreasing performance. And if mission simulation isn't concerned with much happening at the femtosecond scale, it really doesn't care about anything going on at the attosecond scale. So an F64 subsecond integrates very nicely with established algorithms. But rather than use it raw, we define a subsecond new type to enforce the invariant that the F64 must be in the half-open range 0 to 1. And by restricting this F64 to the subnormal numbers, we guarantee that our time always has at least 15 decimal places of precision. Femtoseconds. Easy, right? An int, an F64, a type-safe, user-proof, 128-bit time representation. That doesn't work. Or rather, it's not enough, because there is one thing to ruin it all. UTC, or as I've come to know it, the devil's time scale. UTC cannot be unambiguously represented as a monotonic counter. UTC is an unholy hybrid of International Atomic Time, or TIE, an average of the world's most expensive atomic clocks, and solar time, UT1, which is based on the Earth's rotation. which changes. So UTC is kept within plus or minus 0.9 seconds of UT1 by the inclusion of leap seconds, which are decided about 6 months in advance by the International Earth Rotation and Systems Service, who have the best Christmas parties. So if I give you the time 536,500,836 seconds since J2000, are we at midnight on the 1st of January 2017 or 23:59:60 during a leap second on the 31st of December 2016? And I do say inclusion of leap seconds, not addition of leap seconds, because leap seconds are allowed to be negative. They never have been, but they can be. And the reason for that is that the speed of the Earth's rotation changes over time. Since UTC was introduced in 1960, it has tended to slow, causing us to add leap seconds to stop UTC getting too far ahead of UT1. Since 2020, however, the Earth has been spinning faster. And if that trend continues, well, good luck being on call during a negative leap second, because I guarantee your code base does not handle it. And UTC is just the tip of the iceberg. Astronomers work with time in a minimum of 7 timescales, from good old atomic time to TDB, which is based on a clock that moves with the solar system's center of mass and accounts for time dilation. So on this side, you'll also see Coro, the unsafe rust urchin, marking the 2 extra fun timescales that can't be determined without up-to-date observations of the Earth and Sun. So LOX has to model all of these and transform between them in an ergonomic, intuitive way. So let's start with the representation of the timescale itself. And luckily, every timescale that isn't UTC is guaranteed to increase monotonically. Our base time representation with an I64 second and an F64 subsecond is sound. We just need to pair this data with some indicator of its timescale. We initially tried representing timescales as enum variants, and at first glance an enum seems like a good fit because the number of variants is fixed and it wouldn't require any special treatment when mapping to Python. But we can't specify bounds on enums like we do with traits. We can't define a function that accepts only the tie variant of a timescale enum, for example. And different algorithms have inputs and outputs in different timescales. So instead, we defined a timescale marker trait and implemented it for a dedicated zero-sized struct for each timescale. And with timescale as our trait bound, we can implement a generic time type that combines a delta since an epoch with a scale. And since each timescale is zero-sized, it takes up no more space than the raw timestamp. Now, if, like me, your idea of a good time on Friday is to stay in and read the Rustaceans, you might wonder whether empty types wouldn't be a better fit than zero-sized types. And if, unlike me, you have a life, you might not know there's a difference between empty and zero-sized types, but there is. A zero-sized type occupies 0 bytes. So the compiler can optimize code pretty aggressively, particularly in avoiding allocations where it knows statically we don't actually need any memory. But ZSTs still exist at runtime. So like photons, they have no mass, but they still interact with the world. They can have methods, you can accept zero-sized parameters and return zero-sized values. You can get hold of one and do stuff with it. Empty types, however, are purely type-level constructs. They do not exist at runtime. An empty type is specified as an empty enum, and what can you do with an enum with no variance? They cannot be instantiated, called, or passed around. And this makes empty types ideal as carriers of type-level information. They're labels, essentially. And it seems like timescale is a good use case for this. If we know by the type parameter alone that we're dealing with a time tie or a time TDB, why carry around the scale field even if it does weigh 0? Maybe Einstein was wrong. Like, what if time isn't physical reality, but a figment of Rustaceans' imagination? Unfortunately not. Nature works in mysterious ways, and people voluntarily use Python. And since Python's a dynamic language, Python bindings must be fully specified at compile time. You can't have bindings that take or return times generic over some t, because the Python interpreter can't tell you what t you're dealing with until it's up and running. By retaining the scale field, we preserve the ability to instantiate times dynamically from Python without increasing the memory footprint for pure Rust implementations. When you instantiate a time from Python, we fall back to an enum-based timescale along the boundaries of the library. The variants have no fields, so the size of a pi timescale is the size of the discriminant of the enum, which is platform dependent, but never more than 64 bits, unless you have a stupid number of variants. Heads up that the naming here is somewhat misleading. Dyne timescale isn't Dyne in the sense of it being an unsized trait object. It's Dyne in the sense of instantiated dynamically. And if a Python user tells LOX that their time is in Thai, LOX just has to trust that they know what they're doing despite choosing Python over Rust, and takes them at their word. And at the end of the day, although it's aesthetically pleasing to save a few bits by using zero-sized timescales internally, and as much as I resent Python for slithering over my statically typed Zen garden, eliminating an enum discriminant is not where a space mission simulator gets its performance boosts. There is just so much more headroom in techniques like parallelism and avoiding expensive copies. So I hope that at this point, you're feeling pretty comfortable around the representation of astronomical time as a scale and a delta. And I want you to enjoy that feeling of quiet confidence while it lasts, because we're about to talk about UTC again. Back in the land of shadows, with LOX, we made the decision very early that although we can't cast UTC into the fire, we can contain it. UTC gets a dedicated year, month, day, hour, minute, second, subsecond type, which exists strictly at the boundaries of the LOX time crate, and is treated exclusively as a human-readable I/O time format, which must be converted to a continuous time scale for use in calculations. Now, flight dynamics engineers expect input times, they expect to be able to input times in a format they understand, which is a perfectly reasonable expectation of a highly unreasonable timescale. And LOX does significant legwork to hide that complexity from the user. LOX's UTC type is leap second aware out of the box, and it ensures that each transformation to other timescales is unambiguous. And we achieve that through the leap seconds provider trait. LOX provides a default implementation, which I wrote and experience violent flashbacks about to this very day. We don't have time to get into the implementation in much detail, but I will throw you two pieces of little-known UTC trivia so that you can drop into conversation and make friends. Works, it does. First, UTC is not defined before 1960. So if someone tells you that the birth date column of their database is in UTC, and it's not a service for under 60s, oh boy, are they going to be embarrassed when you tell them. And second, UTC actually predates the concept of leap seconds. But around 1972, people realized that civil time and the rotation of the Earth had drifted quite far apart. So they did what any good software engineers would do. They just kind of backfilled it. Avengers assemble. And these days, leap seconds are always added at 23, 59, 60 on June 30th or December 31st. But the clocks were running 10 full seconds ahead of the Earth at this point, and they needed somewhere to put 10 whole leap seconds where no one would notice. So rather than let the clocks run to 23, 59, 69, they just kind of smeared those 10 leap seconds across the full 12-year span since 1960, making each day a tiny fraction of a second longer in proportion to how the Earth was spinning on that day. So please understand me when I say that UTC is a truly evil timescale. And the rest of this talk will be concerned with how we get away from it. How do we specify timescale transformations? The graph on the right shows how each timescale maps to the others. And some of these appear to have very little in common. So tie to TT is my absolute favorite. Just add 32.184 seconds. This is the kind of simplicity I live for. This is the stuff of dreams. TT to TCG is a linear transformation. But the next edge from TCG to TDB is a four-dimensional transformation, which is more complex, certainly, but this data can be specified statically and compiled into a binary. It comes baked into locks. However, as we already know, conversions involving UTC need historical and upcoming leap-second data. And UT1, being solar time, isn't technically a time at all, but the orientation of the Earth with respect to the Sun. So you might be surprised to learn that astronomers are completely unable to model the rotation of the Earth with enough accuracy to predict how UT1, UTC, and TI will differ more than about a year in advance. There are too many forces affecting how the planet spins about its axis, and the axis moves, and the Earth wobbles about the axis as it spins. And it wobbles around the wobble. This is why we only get 6 months heads up on new leap seconds. That means that we need a current source of Earth orientation parameters based on observed data. And the International Earth Rotation and Systems Service provides standard tables for free, but library users should also have the option to provide their own data sources, particularly where these simulations are running on air-gapped networks. Given our stated goal of an ergonomic and intuitive API for astronomical time, this appears to suck. How can we provide a high-level interface that is convenient to call with whatever timestamp the user has to hand without creating a mess of speculative dependencies for unrelated transformations? If we squint, however, we can just about make out a homogeneous set of timescale transformations. And with Rust, we can fluently articulate this relationship in code. So try to scale is the base trait underlying all of LOX's timescale transformations. It is supremely pessimistic. It assumes that every timescale pair requires an external data source in the form of an offset provider implementation, and that offset provider is fallible. And try to scale doesn't care that tie to TT is a simple addition. It is a hammer, and every transformation is a nail. And we know better, of course. Like most transformations, constant, linear, or four-dimensional, are infallible. And the first step on our journey from blunt instrument to keen edge is to implement offset provider for no-op offset provider, a zero-size struct that does nothing without fail. And this kicks off a process of progressive trait specialization, where each tightening of the trait bounds exposes a more convenient but more situational subset of timescale transformations. The next step is to define to-scale, bounded by an infallible try-to-scale based on no-op offset provider. We don't want to force callers to handle failures that cannot happen. And even better, we can blanket implement to scale for any type that implements an infallible try-to-scale, saving the maintainers the headache of doing it manually. Thank you, Rust. And this process continues to the level of single-scale transformations. Traits 2TI, 2TT, and so on specify zero-argument, infallible methods with default implementations for all pairs of simple transformations. And this is amazingly convenient, and Rust gives us that convenience readably, statically, and without sacrificing the ability to work with time as a homogeneous set. What about the fallible transformations, though? I mean, you've actually already seen leap seconds provider in our discussion of UTC, and leap seconds provider is, in fact, a specialization of offset provider. And we do the same for the UT1 tie pairing, which depends on data derived from observed Earth orientation parameters. And delta UT1 tie provider is itself a specialization of offset provider, and try to UT1 is a specialization of try to scale over a delta UT1 tie provider. There are no 2UT1 or 2UTC traits because they are fundamentally fallible operations. And putting it all together, we have a collection of traits that allows LOCs and third-party users of the LOCs time crate extraordinary flexibility to design types and call signatures based not just on the concrete timescales that a particular algorithm requires, but on the graph of timescale transformations. So rather than saying, give me tie, we can say, give me any infallible path to tie. You can say, give me a path to UT1 and the observed data to traverse it, or you can say, I have observed data, give me the path that consumes it. And that is how you model all of time in Rust. So thank you so much for listening. You can find LOCs on GitHub at the link in this presentation. For the YouTube crowd, I will bat my eyelids at the organizers and ask them to put a link in the description. You can find more of my work at howtocodeit.com or reach out to me directly at angus@howtocodeit.com. And I think we have some time now for Q&A, but please remember, I am not an astrophysicist. If you ask me questions too far from Rust, I reserve the right not to publicly embarrass myself. Thank you.
Any questions?
Love it.
Great talk, thanks. Firstly, I'd say that brings back a lot of PTSD from, and you didn't even have to mention coordinate reference frames, which I'm assuming is going to be a follow-on talk.
Oh, it's in there. LOCs has the full coordinate transformation system.
I guess my question would be on time versus there's hi-fi time and a couple of others that are also being used in the aerospace Rust community. Is there a big difference? What are the sort of differences? Do you know?
Yes, hi-fi time we took a good long look at before we started this work. And I have to tread carefully here because the reasons for not just using hi-fi time come directly from a qualified astrophysics. Hi-fi time, for one particular transformation, I think it might be TDB, TCG, but please don't quote me on that, uses a fast algorithm that they claim to be accurate to a certain degree, and this particular colleague of mine disagrees that this faster algorithm is in fact accurate to that degree. Additionally, we wanted to build in the ergonomics to operate on this graph of timescale transformations, rather than sort of the more stepwise approach that hi-fi time tends to adopt. Good question, thank you.
Any more questions?
First, fascinating talk. Thank you very much. I'm more curious about your work and project on the larger scale, let's say. So, how your cooperation with ESA looks like, and what are the next milestones? Where are you heading?
Yeah, I can talk at a high level about how the project is organized. I'm quite fortunate in not having to meet with ESA directly. I just get to stay in my code cave. But this was a pitch put forward by the Libri Space Foundation, who had identified a key issue that I touched on in this, where existing open source simulators are either extremely dated or require a huge amount of extension to get them to do what you need from modern missions. They put together the Libri Space Foundation launched their own scientific missions, and they run a lot of smaller missions for other even smaller players. And they needed software that would better support their own use cases. Speaking to a lot of people in the industry, and particularly people working for space startups, it's a very common problem. And so they put a tender and a pitch together to ESA to try and do something about this. ESA provided, I think it was about $250,000 in funding for it. The project was run as a team of 3 or 4 developers who've been working on it over the course of, it's probably been about 18 months, maybe coming up on 2 years at this point. And it's currently in the process of final review with ESA. So me being here today, I'm having a much better time than some of the rest of the people on the project. Does that answer your question? Fantastic. Thank you.
Yeah, a brilliant talk.
Thanks.
This may be too much of an astrophysics-y question, but what kind of timekeeping is used on board satellites and rockets for their onboard guidance systems? And is there any interest in using locks in those embedded applications and like using these time transformations?
They are performing fundamentally similar operations. The base time scale that they kind of use a lot simultaneously. Everyone's reference time is TIE. That is what the atomic clocks are defining. And it's also TIE is what GPS is based on as well. And that's GPS time I'm very glad I haven't had to work with because it's hideous. It's denominated in weeks. It's almost as bad as UTC. So TIE is the reference time. In plotting something like a trajectory, in plotting maneuvers, if you need to maneuver around an object, you have to do what the man who asked the question in the front row here touched on, which is reference frame transformations. And that necessarily involves a lot of switching between different timescales. That is why something like Python isn't ideal for doing, well, never mind about isn't ideal. Don't do anything real time with Python. Locks, certainly being in the much closer to the metal, would be a far better choice. It's not something we have specifically approached because it was way outside the scope of the ESA brief, but it wouldn't be a big stretch to adapt it in that direction. Thanks.
I'll ask another one. Have you got any commercial partners with sort of the ESA funding and project?
Not that I'm aware of, but if you drop me an email, Angus at How to Code It, I can put you in touch with the project lead if you'd like to know more.
Cool.
Any more questions?
Hey, yeah, towards the start of the talk, you compared Rust to Python and Java, and then about halfway through you said, oh, Fortran, which is a lot of people are still using, right, for lots of different applications in space and otherwise.
Yeah.
Do you have any comment on, I guess, the comparison in performance between Rust and Fortran for those kind of numerical algorithms, and also then more widely the use within the community? Because I think a long time ago, more people learned Fortran, and now we have different languages and options and different kinds of computers, and people are learning different things. So is this something that's maybe going to be a cultural shift over the next 10 or 20 years?
That is a really interesting question because people using Rust, people using Python, people using Fortran, they tend to, at least for the sake of space mission simulation, fall into 2 camps. You're either approaching it from an academic perspective or you're approaching it from the perspective of needing to complete a specific mission or launch commercial payloads. In terms of how Fortran performance compares to Rust, they ultimately compile right down to machine level instructions, so you can theoretically achieve exactly the same performance for the machine you're running on. You don't get the memory safety with Fortran. You get no safety guarantees whatsoever, and you certainly don't get the ease of code that is very readable after you've written it. And I've used the Fortran implementations for some of as reference implementations for some of Deloc's work, and it's a bit like an archaeological dig. So I see Rust's advantages over Fortran being the safety and readability rather than the speed so much. Fortran, yeah, the world was a lot less fragmented back then. I personally don't see academic physicists adopting Rust on a large scale for their simulations, typically because there aren't hardcore performance requirements. Like, physicists, depending on what they're doing, can be quite happy to just like leave the simulation to run and we'll come back to it tomorrow. The commercial side of things, people who are actively running missions, people who need to get things done on commercial deadlines and who need to operate real-time systems as well, I think Rust is almost certainly going to dominate that corner. Thank you.
Any more questions?
So in this talk, you mainly talked about time, but I guess you're also simulating objects. Is that correct? So, and I appreciate that this might be a total guess. What would you say is the theoretical limit of how many objects you could simulate at any one time?
How big is your computer?
Very good point.
It's strictly so. LOX being a library, it will eat up as many resources as you give it. In particular, a lot of astrodynamics falls into the category of embarrassingly parallelizable problems. The more cores you have, the faster it can get, the more throughput you can get. So it depends on the machine entirely.
Any more questions?
My question is just, I'm curious about how you got into this, because it's quite a niche field. Your background was slightly different to probably the other people you were working with, so I'd be interested to know how you came.
Nepotism, I think is the answer. By sheer chance, I happen to be very good friends with someone who works for OneWeb, which is Europe's sort of attempt at a Starlink. He, in turn, knew the project lead for this project, who was very experienced at having written several of them himself with the problems posed by existing astrodynamics libraries in other languages, and very excited about the opportunities Rust could offer. I happened to know Rust. I'd done a lot of Rust work previously, and my friend put me in touch. I'm ashamed to say, but how all the great astrodynamical success stories happen.
Diverse set of skills.
Sorry, but in that sense, is LOX looking for contributors, or what would be?
That's a very good question. So as I mentioned briefly, if anyone didn't hear that, we're wondering if LOX is looking for contributors, and thank you for asking the question. I mentioned that it's currently undergoing its final review, and basically what comes out of that review and the scope for further development will determine like how many additional contributors are needed, or whether it's enough in its current iteration to go into more of a maintenance mode. So drop me an email. Again, my email address is up there, and I can put you in touch with the lead once we've got more information. Thanks.
Hi. I'm not sure if I got it from there. Does this support like a sort of lunar time or Martian time and things like that, or is it purely just sort of Earth-centric?
We have not gone anywhere near lunar time yet in the LOX time crate specifically. However, we do have all the ephemerides for the other planets and the celestial bodies worth mentioning. So it's not a particularly large leap to plug those in and support missions beyond orbit. But one of the most compelling use cases for this was the idea of flying multiple satellites in conjunction rather than missions further from Earth.
Thank you for the talk. What is the situation regarding, with these open source simulations regarding compliance and regulation in the industry?
Good question. Very good question. This is why it's often hard to get hold of space simulation and, in general, space-related technology from the US, because they have extremely restrictive export controls. It's an act in the US called ITAR, and it makes it very difficult for anyone who isn't a US citizen to work with. Equally, ESA is a very, very large and very bureaucratic organization, which makes open sourcing anything that they already have very challenging. Like, it is genuinely faster to build something from scratch than to try and figure out what existing things of ESAs can be published and released, which was very much the spirit of this. So this is released, I actually don't remember the exact license, but it is a free and open source license, as long as you include the copyright notice. There's no further restriction on that whatsoever. Thank you. MPL.
Any more questions? Oh.
Amazing.
This might be too complicated, but how does relativistic time work? Because doesn't that depend on where you are and where everything else is?
I have my what is time slide. I've left out my what is relativity slide. The good answer to that is ask a proper physicist. I have the definition mathematically of the algorithm that supports relativistic transformations. I have the static data that allows me to do it. Beyond that, I am a monkey with a keyboard. Can't help you.
Any more?
One over here.
Yes.
Would you consider logs viable as the physics engine for a game? So if I were to try to build something with Bevy using logs, would you say that's a good idea?
If you wanted to build a space mission simulator with Bevy, I'd say step right up. But LOX itself does its linear algebra, I think, using GLAM. So at the point where you are considering something to power a game, I'd say probably stepping down to the level of just that linear. In fact, Bevy might use GLAM. I don't remember if they've implemented their own one. But I would start there, unless you specifically need like astronomical transformations.
Any more questions? Nope. Thank you.
Thank you very much. Thank you.